All right, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. We're getting towards the end of the course. This is the second to last week of class, and next week will be our final lectures of the semester, with the final exam followed the week thereafter. All right, so we're wrapping things up. We have one or two more lectures on pipe friction and pipe losses. Then we'll have a lecture or two on drag and lift, and that will be the culmination of the course. So today I just want to continue on with some topics we saw from last time. I wish to continue on and look at a few problems and a few examples on pipe losses, minor losses, major losses, etc., but mainly minor losses. I want to consider that here. Okay, so first again today, all we're really going to be doing is working through some examples. So let us consider a few examples. If I can manage to get my pen proper. Let me just call this example 1. All right, so let us consider example 1. Now, I'm going to have a water tower or a tank. I guess a water tower is probably too strong a word for this. Just a slightly elevated water tank at a certain height, and it will be passing through a pipe and a valve. All right, so let's consider this tank. I'm going to have a water tank here. And it's going to be an enclosed tank with a vent at the top, thus allowing this to maintain atmospheric pressure throughout. Well, up to the surface of the water anyway. So I have a tank here and a vent. This allows us to use atmospheric pressure for our problem. And then I'm going to have a pipe coming out of this. So all of this is given. Let me draw out the whole system here. All of this is given. I have a pipe. There will be a valve at the end of it. So some sort of valve. Let's draw that kind of like this. So some sort of valve. However you want to draw your valve is fine. And then coming down here, there will be another pipe, and then this thing will go vertical. And I'm also told that there is a certain water spout that emerges from this. And so let me draw the fluid. This will be water. Here will be the water surface, the peak water surface. And again, it's going to be the air pressure here is going to be normal atmospheric pressure, again because there is a vent in the tank allowing water in. And then I'm also told that in this setup, when I open the valve, the water streams out or rises to a height of 3 inches above this point here. So not that high above, but that's okay. And this whole thing is full of water, and the pipe here is horizontal. Then let me label some dimensions. We're going to need these. The whole thing here is going to be 32 inches long. Will be 32 inches long. Let's say from our this is going to be our datum line here. The center line of the pipe is going to be our datum line. And this is our datum. And from the datum to the bottom of the tank is going to be, let's say, well, this will be 18 inches. And from the top of the tank to the bottom of the tank will be a height of 27 inches. And then from the datum line to the top of the spout here is going to be 2 inches, or to the top of the pipe here, and to the top of the water jet is just going to be another 3 inches. So not that much further. And then some information about the system. I'm also told some information about the system. The fluid is going to be a water, ordinary water. The pipe diameter is going to be 1/2 inch. So I have a 1/2 inch diameter pipe. It is galvanized iron. There are threaded fittings. And because it's water, I know that I'm going to use a dynamic viscosity, mu W, just the dynamic viscosity of water. And this is going to be 2.34, and I'm going to be using English units here, times 10 to the negative 5 pounds second per feet squared per square foot. And then the density of water, the rho W, is going to be 1.94 slugs per cubic foot. 1.94 slugs per cubic foot. Per cubic foot. And I'm given all of this, and I want to find KL, the minor loss coefficient, essentially. Okay? So I want to find the minor loss coefficient. All right. Let's say of the valve. Of the valve. Of the valve. So let us look at this. Now, we want to look at how this is going to work. Every piece of information here is going to be critical. This problem is more complicated than it seems, because what's going to happen here is I'm going to have losses at a whole bunch of different locations. First, I'm going to have my major losses that will be along the entire length of the pipe. The entire length of the pipe will have major friction losses associated with it. Then I'm going to have minor losses at a variety of locations. One, I'm going to have a minor loss where the tank enters into the pipe. Then I'm going to have a minor loss at the elbow here, the minor loss at the elbow here, and a minor loss at the valve. So I have 4 different localized instances where minor losses will occur. Now, I will be, since the bends themselves are something that I can look up. The bends and the entrance, these are something that I'll be able to look up in a table, but the valve is something unique. I'll have to actually calculate that one. So again, we're going to look up losses for bends and entrance in a table. Okay, so let's work through this. Okay, so the first thing I want to do is I want to find my velocity. Okay, so let us compare let me actually label some points first. That might be useful. Here, I'm going to label my points, and maybe I'll do it in orange or something so it'll stand out. I'm going to label the top surface of the water here, point 1. Then next, I'll label the point here at the end of the pipe, point 2, and then I'll label the top of the water spout here, point 3. Okay? So I want to determine the first thing I want to do is determine the velocity at 2. Find the velocity at point 2. Basically the velocity of the water right when it leaves the pipe. Of water at point 2. And the reason I'm starting there is that at that location, this would be a lot easier if I knew the velocity at some location. And what's nice about that is, what's nice about point 2 is between point 2 and point 3, there can be no more friction losses. This is just water. This is just a water jet in air. There are not going to be any substantial friction losses there. There is no pipe. There is no pipe there for friction to exist. There are no bends or fittings or anything else. So I can find the velocity at point 2 just based on the height difference there. Okay, but I'm gonna write out the whole Bernoulli and illustrate how I would find the velocity at 2. So P2 over gamma. So I'm going to set up a Bernoulli between points 2 and 3. Between points 2 and 3. And then P2 over gamma plus V2 squared over 2G plus Z2 is going to be equal to P3 over gamma plus V3 squared over 2G plus Z3. Now, I can start eliminating terms. So these are both going to be at atmospheric pressure, so I can eliminate the two pressure terms. This will be 0 and 0. Then the velocity at point 3 is, well, it's obviously at the peak of its height, so velocity there, that also will be 0. Then I can simply do, now this is very simple algebra of the type we've seen many times throughout the course. And this, I can just solve for V2. V2 is going to be equal to the square root of 2G times 2G times Z3 minus Z2. Z3 minus Z2, and then this is equal to the square root of 2 times 32.2 divided by 3 over 12 feet. Again, it is important, as always, to use consistent units. 32 feet per second squared times 3/12 feet, or just 3 inches converted to feet. And this comes to a V2 of 4.01 feet per second. So I've now found one critical piece of information, and this is going to be my velocity at point 2. So I now know my velocity at point 2. Now, let me go back and illustrate something else, though. Let us consider something here. What do we know about this pipe all the way along here? What do we know about the diameter of the pipe? Yes, exactly. So the diameter is constant. And if the diameter is constant, what do we know about the velocity? Exactly, the velocity is also constant. So as long as this is full of an incompressible fluid, now if it was full of some highly compressible gas or something like that, then we couldn't do this. But because this is an incompressible fluid, as we know from control volumes, that there has to be, if we could define a control volume as this whole pipe here with one boundary here and one boundary here, and there has to be just as much mass entering this end of the pipe as leaving this end of the pipe. And the only way that can be true, the absolute only way in the universe that can be true, is if the velocity is equal here, 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 here. Everywhere the velocity is the same. That velocity is not just going to be velocity 2, but velocity v. Velocity all the way along the pipe. Velocity all along the pipe. So even though there's going to be changes in height, even though there's going to be loss from friction and from pipe friction and from valves and bends and everything else, in reality, that energy cost is going to have to come from somewhere. And where is it going to come from? Where do you think that energy loss is going to come from? If we looked at Bernoulli, remember, let's go back to Bernoulli. We have different locations where we can take energy from. We could take it from height, but really that's not really something we can really choose. Again, where it's going to come from is the pressure. The pressure in the pipe is what's going to pay the toll to get the water through the pipe. So I've used this analogy before, where we have every inch of pipe, every millimeter of pipe has a certain toll that the water has to pay, or any fluid has to pay, in order to go through. That toll has to be paid somehow. And more often than not, it's paid for in pressure. Now, if you have a system with a changing diameter, then things can change perhaps. But as long as diameter is constant, any frictional losses will be paid, and as long as the pipe is both level and of constant diameter, the only place, the only location, the only way that toll can be paid is via a drop in pressure. Okay, so we know now that we have a constant velocity all the way along the pipe, and then we can simply, and through this, we can calculate one constant Reynolds number that will apply to the entire system. So step 2, calculate Reynolds number. And this will be a constant Reynolds number for the entire pipe. For the entire pipe. And here the Reynolds number will be equal to rho VD divided by mu. And this will equal 1.94 slugs per cubic feet times 4.01 feet per second squared. Oh, sorry, not feet per second squared, just feet per second, times 0.5 divided by 12 feet, again, using consistent units, and a mu, our dynamic viscosity, of 2.34 times 10 to the negative 5 pound second per foot squared. Pound second per foot squared, and then this is going to be 13,852. Wow, that's really bad. 13,852, and then this then of course is greater than 4,000. So what do we know about this? Why did I pick 4,000? Turbulent, yes. Turbulent. Kind of like this time of the semester. Turbulent. So what does that mean? How are we going to get the friction factor then?
Moody chart.
Moody chart, yes, Moody diagram, Moody chart, Moody diagram. Hopefully it doesn't make you too moody on the exam. I'm so sorry. No, I'm not. Anyway, step 3, I want to find the friction factor in the pipe. And I've gone over this a million times, so I'm not going to go in this in detail. We could pull up the Moody chart and show you how to interpret that again, but we've already gone through that several times. So I'll just list what inputs we use and what output we'll get out of it. So calculate the friction factor. And I'm going to say that our friction factor epsilon is equal to 0.0005 feet. And then epsilon over d. And this comes from the galvanized, we were told that it was back here, we were told that it was galvanized iron. So that's where the 0.0005 feet comes from. Epsilon over d then is going to be equal to 0.0005 feet divided by our diameter of 0.5 inches. Is there something wrong with that?
Yes.
What's wrong with it? But the diameter is 0.5 inches. What's the problem? Oh, right. I need to divide by 12. Yes. 1 foot over 12 inches. Very important to use consistent units. And this comes to 0.012. And then finally our Reynolds number, which we just calculated, is equal to 13,852. And if I take these two pieces of information, both the epsilon over d and the Reynolds number, and put them into the Moody chart or the Moody diagram, I will find that the friction factor is equal to approximately 0.043. 0.043. 0.043. So we're not done yet, but that is again the major law. That is the friction factor, which is what we will use to calculate the major losses in our system. Okay. Now I'm going to write out the complete energy equation with losses included now. So I guess this is going to be step 4. Consider energy equation and I'm going to do this between 1 and 2. With losses included. Okay, so let's do that. And I'm going to have P1 over gamma plus V1 squared over 2G plus C1 is equal to P3 over gamma. Actually, sorry, between 1 and 3 is how I have this set up. Sorry about that. Plus P3 over gamma. We could also do it with V2, but I just have it set up for V3 here. Plus, the nice thing about using V3 is that the velocity there will be 0. Plus V3 squared over 2G plus Z3. Am I done? But I wrote out all of Bernoulli. Oh, fine. I'll put my losses in there too. Okay. It's Friday. I thought I could get away with being lazy. HL major, major head loss, plus HL minor, minor head loss. You're not letting me get away with anything today. Anyway. So let us look now at the major and minor losses. So I've set up my equation, although I need to start canceling a few things out. So I'm going to say, well, the pressures, these are both going to be 0. And V1 is also going to be 0 because we're looking at the energy at the surface, the upper surface of the water tank. We could look at things at the entrance to the water tank or something like that, but the problem with that is then we would have some energy term there and we'd have some velocity term there and things would get more complicated. Oh, and also we can get rid of this here. Oh, look at that. Both our velocities are going to be 0. That's very useful. Both of our velocities are going to be 0. We have the velocity at point 1 is 0 because it's on the upper surface of a tank, and the velocity at point 3 is going to be 0 because that's the peak of the water spout where it's flying, or it's flown up as far as it can. Okay, so from this, we now have an equation that we can use going forward, and I can say then that Z1 minus Z3 is equal to HL major plus HL minor. So this is a further equation that we'll be able to use in our following analysis. Okay, so we know that the difference in heights will be equal to the major loss plus the minor loss. Let's say, I guess this is step 5. Set up equations for losses. For losses, and this is, I want to be consistent, so I'll just call this step 5. Write that. Set up equations for losses. And first I'm going to consider major losses. Or the major loss. And this is going to be, so HL major is equal to FLV squared, FLV squared over 2GD. And this is equal to 0.043, the friction factor that we got previously, times our length. And the length is going to be the entire length here. It's going to be, let's back up here. It's going to be this 18 inches plus this 32 inches plus this 2 inches. However, it's not going to include this length here or this length here. I'm talking only about the actual length of the pipe. Okay, so it's only the actual length of the pipe. So it's not going to include the height because it's not going to include the height in the tank because that's not part of a pipe. And it's not going to include the water spout because that's also not in the pipe. Now we will later consider the minor losses from the bends and things like that, but for now we're only looking at the major losses. So 0.043, and our length is going to be 18 plus 32 plus 2 divided by 12, that many feet, times our velocity of 4.01 feet per second squared. Feet per second, quantity squared, and then divided by 2 times 32.2 feet per second squared times the diameter of 0.5 over 12 feet. 0.5 over 12 feet. All right, so we have that. And if you go and put all that into a calculator, you'll find that the HL major, the major head loss, is going to be 1.12 feet. 1.12 feet. Next, I want to calculate, so that is a fixed quantity. It doesn't depend on the minor losses. It doesn't matter how many valves or fittings or whatever else I have in between there or I have along the pipe. As long as I have this pipe here, as long as I have a pipe of this length with this velocity and this fluid traveling through it, we are going to lose 1.12 feet of head between the end of the tank and the start of the water spout. Then minor losses. And when I say head loss in feet, I literally mean that in feet. In other words, that if I could replace that pipe with some sort of magical frictionless pipe and there were no, and the fluid itself was magical, some sort of magical frictionless fluid, that would also be the water spout would be that much higher there. So let's set up our equations for losses. Then minor losses. Let's look at our minor losses. Minor losses. Well, I know that HL minor, if we remember from last time, the minor head loss is going to be equal to the summation of KL times V squared divided by 2G. So basically all of the individual KLs times V squared over 2Gs. Then let's consider this. Now, let us look at this. However, one thing I can do, this equation is set up, note, let's put a little note here. Note, this equation is set up to handle various velocities along the path. Set up to consider changes of velocity along the path. Here, our velocity is constant. So our velocity here is constant. So we can change this formula and make it a little bit easier to work with. Therefore, we can do, instead of just this, I can actually say V squared over 2G times the summation of, I can pull the V squared over 2G out. So times the summation of KL is equal to HL minor. And that there can be useful. And again, the point for this is I can only do this because the velocity is constant. Now, if you had a pipe that was going through a whole series, let's say we had a pipe that was, I don't know, going through a change in diameter. Like we went through something that had, maybe we had a pipe that was constantly changing its diameter or something like that. And in that case, if we were analyzing the entire length of a pipe, if it was for some reason needing to change its diameter, well, at every point we would need to consider the velocity at that point. But in this system, our velocity is the same all the way along. So in terms of our summation here, our velocity is constant, and obviously g is constant. Now if you are wanted to be incredibly technical, you could argue that if there's a change in height, the g is going to be slightly higher or lower at one elevation than another. But let's just say if you're designing your system to that type of tolerances, well, you're going to have a bad day. These equations are not that precise. They are good enough for design in most cases, but if you're trying to design a water system or a water delivery system or a pipe system using, 0.001% accuracy or something like that, you're going to have a very bad time. even from, when the temperature of your water increases by 0.5 degree Celsius, that will screw up all your perfectly balanced calculations. So that's why we have factors of safety in normal engineering design. Anyway, so let's consider this. Now, I'm going to again say that again, I am going to use, actually, I set up my equations here, so I'm going to add another step. Step 6. And I'm going to say, calculate sum of KL expression. Now, let us consider this. I'm going to say the sum of KL, and we need to look at every source of minor loss along this thing. This is going to be equal to the KL at the entrance, the loss coefficient at the entrance. So that means where the pipe begins, where the water leaves the tank and enters the pipe, plus KL at the elbow, the first elbow or the first bend, plus KL at the second elbow, plus KL of the valve, and that is what we're looking to calculate. So plus the KL of the valve. Now the rest of these we're actually just going to look up in a table. I find these values in chapter 8 of our text, and what I'm going to find is I will find this is 0.2, this is 1.5, 1.5, and this is just our unknown KL valve. And if you look in your text, there are certain assumptions that you need to make, and the assumptions here that I made for this is that we have a smooth entrance. In other words, it's not like a jagged, when I say a smooth entrance, I don't necessarily mean the material itself is smooth. It can all be galvanized iron. But what I mean by smooth is that it's not, say, like a jagged rusty metal pipe just stuck in the side of the tank wall or something like that. It's a smoothly crafted entrance that will allow water to smoothly flow past. And then for both of these are 90-degree threaded bends. Depending on the type of bends, whether you have threaded or welded bends, you can have, and some other factors as well, you can have different KL values. And again, these are actually determined experimentally. These are determined in a lab. And so you can't calculate, perhaps you could actually calculate these theoretically based off of some very advanced, finite element modeling, fluid dynamic simulation or something like that. But these are, so theoretically, I suppose you could calculate some of these KL coefficients just based off of a computer or something like that. But in terms of the calculations that you can do with pen and paper, that's definitely not going to be something you can do. So in terms of most design, when you want to actually design or calculate the losses, you go and look up the results of some experimental process. You look those up in a table. And when I look these up in a table in the text, these are the coefficients that I found. And don't worry, on the exam, any tables or values needed will be provided. Well, if I was exceptionally evil, I could just say, well, here's 100 possible values. Please memorize them. I just hear nervous laughter. Okay, so all of this then will collapse to the summation of KL is just going to be equal to 3.2, not 32, 3.2 plus whatever KL the valve has. And that is equal to the summation of KL. 3.2 plus the summation of KL. And I have one more step, and that is to solve for KL valve using the energy equation. Step 7. Step 7, again, will be to solve for KL valve, our final result. Using energy equation and the previous result. And it's going to be like this. So I'm going to have the previous energy equation between 1 and 3, and this is Z1 minus Z3 is equal to HL major plus HL minor And our change in height is going to be 40 inches. So Z1 minus Z3 is 40 inches, and divided by 12 inches per foot to use consistent units. 12 inches per foot. And this is then equal to 1.12 feet, the major loss, plus our expression for HL minor. The KL, the summation of KL, is 3.2 plus KL valve, and then times our V squared over 2G, so 4.01 feet per second squared, divided by 2 times 32.2. 2 times 32.2 feet per second squared. And close parentheses. And then if you work through the algebra and solve all the way through that, you will find that the KL of this valve, the final result that we've been after for the last, half hour, KL valve is simply going to be 5.67. The KL for this valve is equal to 5.67. Not equal, nope, not feet, not inches. It is a unitless number. It's just a very simple system there, and that's it. All right, here. Okay, so I think I have that here. And I think, let me see here. There is another example that would be nice to work through. You want me to work through it? Okay. Well, let's see. I might stop this really quickly here and then restart in a second. So, all right, that'll do it, and thank you.